problem number 1 on the tear-off sheet. So problem 1 reads, a rectangular page is to contain 24 square inches of print. The margins at the top and the bottom of the page are to be 1.5 inches, and the margins on the left and right are to be 1 inch. What should be the dimensions of the page so that the least amount of paper is used? Let x and y be the width and height of the print area as shown. So here's the print area as shown, x and y. And we know that, let's see, the margin at the top, okay, so then this here, this margin, is 1.5. That's 1 1/2. And the same thing here at the bottom. So this is 1.5. So top and bottom are 1.5. And now, the margins on the left and the right are to be 1 inch. So we know that this is 1 and that is 1. Okay, so now, what should the dimensions of the page be so that the least amount of paper is used? So we're looking at this big page here, and we want to find the least amount of big piece of paper that we need to minimize this. So now we want to minimize the big piece of paper. However, we know that so let's call it, we have two areas. Area of the small, so I'll call that this piece here. That's x times y, and we know that's 24 square inches because they give that to us. Okay, so we know that's that. Now we have area of big, so that's the big one. That's going to be, so we want to find the length of this right here, the width. That's going to be this x, so that's going to be this length, plus this piece and this piece. But each of these pieces are 1, so we have 1 plus 1 is 2, so then we have that's x plus 2. So x plus 2 times, now we want to find the length of this. Well, we know that this length is this length y plus this piece and that piece. But this piece is 1.5 and this piece is 1.5, so 1.5 plus 1.5 is 3. Therefore, it's y plus 3. Okay, so that's what we want to minimize, this function here. However, we have y plus 3. But we can do some substitution because we have the area of the small is x, y equals 24. So this implies that y is equal to 24 divided by x. Okay, so we can go ahead and plug in y in here. So now area of big in respect to x now is x plus 2 times 24 divided by x plus 3. Okay, let's go ahead and work with this up here. Okay, we want to take the derivative of this, but first I want to go ahead and do some algebra and simplify this. So let's go ahead and distribute. So we have area of big x is equal to, it's going to be 24. It's going to be plus 3x. That's going to be 2 times 24. So that's going to be 48. Okay, and then 2 times 3, that's plus 6. Okay, so then area of big is equal to 30 plus 3x plus 48 divided by x. Okay, so we want to minimize this, so let's go ahead and take the first derivative. So, a big prime x, the derivative of 30 is 0, the derivative of 3x is just 3. The derivative of 48x is going to be minus 48 divided by x squared. Alright, let's go ahead and put this into one fraction. Okay, so the LCD here is x squared. So that's 3x squared minus 48. Okay, so now we have this. We're going to go ahead and set the numerator and denominator equal to 0. So 3x squared minus 48 is equal to 0. That means that 3x squared is equal to 48. And then divide both sides by 3. So we have x squared is equal to, well, it's 48. That's 2 times 24, and 24 is 2 times 12. And that's 3 times 4. So we're left with 4 times 2, 8, and then that's 16. So this whole thing is 16 here. Okay, so now take the square root of both sides. And x is equal to, when you take the square root of both sides, you get plus or minus, but minus doesn't make sense because we're dealing with the side of a rectangle here. So that's going to be x is equal to just 4. Alright, so we have x is equal to 4. Let's go ahead and put that on an underline. We have 4 here. Also, there's bounds for that x. That x can either be 0 or 24, and not including 0. If you plug in 0, then you get 0's area, but it could be 24. So let's pick a test point between 0 and 4, and 4 and 24. So let's say I'll pick 1, and here I'll pick 5. So then I want to go ahead and plug that into my first derivative and see what sign I get. So plugging in 1, first test point, plug that into here. I'm going to get negative 48 divided by 1, that's a negative, so a negative number. That's decreasing. And then a prime b of 5. So plug 5 in here, 5 squared 25. 25 times 3 is definitely bigger than 48. So that's a positive, and then divided by a positive is a positive number. So that's increasing. So in order for it to go decrease, increase, it's got to have a min. And that's exactly what we want. We want to find what should be the dimensions of the page that the least amount of paper is used. So that's the min. So it means when x is equal to 4, we have the least amount of paper used. And if x is equal to 4, what's the y? Okay, so if x is equal to 4, then y is equal to 24 divided by x. So that's 24 divided by 4. That's 2 times 12. And 12 is 4 times 3, so that's just 6. So it's 2 times 4 times 3 divided by 4. Therefore, y is 6. So that gets... Okay, so the function to be minimized was this one. Let's go ahead and circle that down. That was to be, well, it says maximized, but it's minimized. The constraint here was x is between 0 and 24. And then the x inches is going to be 4, and the y inches is going to be 6. So this is 4 inches and 6 inches there. And then we want to find the dimensions of the page. So now we want to find the dimensions of this whole big page here. But we know that we can find the dimensions of the page because we know that this piece right here, x plus 2, is going to be 4 plus 2. So then, here, let's put dimensions of the page. So dimensions of the page is going to be this x, well, this whole piece here, which is our x plus 2. We already have x, that's 4, so 4 plus 2 is 6. It's going to be 6 inches by, and now this from here to here, that's going to measure y plus 3, but we already have y, that's 6, so 6 plus 3 is 9. So then the dimensions of the whole page is going to be 6 inches by 9 inches. And that answers that.